Welcome to the 7th installment of the probability course notes. This is going to be about the binomial theorem. And there's an alertness bonus point, right? For those of you who noticed in the last 3 or 4 PowerPoints the probability typo, I finally was alert enough to fix that myself. So let's talk about the binomial theorem. We're going to start off talking about probability trees. And hopefully we'll tie in the two topics. So a probability tree works when there's kind of two things that can happen, heads or tails, for example. So if we're going to flip 4 coins, we can model the coin flips with a probability tree. And so there you go. And then to answer the question, we can follow the branches on the tree. So what's a probability tree? Probability tree is a directed graph. That means directed means that I can only traverse in one direction along the tree. So this represents the first coin flip, where only two things can happen, heads or tails. And depending on whether heads or tails has happened, my second coin flip either happens at this vertex or this vertex. So it's a graph because we just have edges and vertices, and it's directed because we have only one way that we can go. And so then the final outcomes from flipping 4 coins are down here. And you can see the 16 outcomes are listed along the bottom of the tree. So to answer the question about what's the probability that exactly 3 heads occur, well, we traverse all of the places, all of the paths to where there are 3 heads. So 1 heads, 2 heads, 3 heads, then we've got to switch over to tails, right? So that's why these are marked in red. Because this path leads to 3 heads. And then if I have 2 heads to start and then a tail, then I need to go down the heads path to get heads, heads, tails, heads. And there's a third path here where I alternate heads, tails. Sorry, heads, tails, heads, and I have to go heads so that I have 3 of them. I do have the graphic right. And then finally, if I start off with tails, then all 3 of the last coin flips have to be heads. So the answer is there are 4 16ths. Why 16 in the denominator? Well, there are 4 coin flips, so there are 2 to the 4th outcomes. Since each outcome has each coin flip has 2 outcomes associated with it. If I do it 4 times, it's 1/2 to the 4th, or 1/2 to the 4th, which is 16. Anyway, this does reduce to 1/4, which is the probability. And this 4 will be important to us when we look at Pascal's triangle and the binomial theorem. Here's the tie-in with probability trees and the binomial theorem. So you may not recognize the binomial theorem, but you've probably done it under the guise of Pascal's triangle. They are the same thing. And in high school students, when they see it, they tend to see Pascal's triangle to expand a binomial like x plus y quantity to the 4th. Pascal's triangle starts with a 1 at the top, and then it has 1s down the left and right diagonals. And then the way I find the numbers in Pascal's triangle is, for example, to find 3, I add the 2 numbers above to the left and above to the right. And that's how I end up with the next row of Pascal's triangle, as long as I know the previous row. So the 4th row of Pascal's triangle, which I'm going to use to expand x plus y quantity to the 4th, it's going to start with a 1, then I add the 1 and the 3 to get 4, and then I add the 3 and the 3 to get 6, I add the 3 and the 1 to get 4, and then it finishes with a 1. So if I want to expand x plus y quantity raised to the 4th power, I know that there's going to be a y to the 4th term. And I know that there's going to be an x y cubed term. And I know there's going to be x squared y squared, and there'll be an x cubed y, and finally there will be an x to the 4th term. Okay, I know that these patterns all have to exist. The question is, what are the coefficients, right? What are going to land in these slots? What numbers are going to land in these slots? And the answer is the numbers in the fourth row of Pascal's triangle. So if I'm expanding something to the fourth, then I use the fourth row of Pascal's triangle, and I get, there'll be 1 y to the fourth term. There will be 4 xy cubed terms. There'll be 6 x squared y squared. There will be 4 x cubed y cubed, and there'll only be 1 x to the fourth. So that's what we mean by using Pascal's triangle. The binomial theorem is the exact same thing, except that we use these choose notation, these binomial coefficients, to find the row and to find the coefficients. Okay, so if we switch back to this view, right, what we're saying is that this coefficient, since we're in the first row, and we start counting at 0, this term is 4 choose 0. All right, and then this coefficient is 4 choose 1, because there are 4 choose 1 different ways that will end up with that pattern, that xy cubed pattern. And this number is 4 choose 2. And this is 4 choose 3. And this one is 4 choose 4. So there's a couple of things to notice if you're not real familiar with these binomial coefficients. 4 choose 0 always equals 1, and 4 choose 4 always equals 1. These, where I'm doing a number choose 1 or a number choosing 1 less than itself, these are always that number. So 4 choose 1 is 4, and 4 choose 3 is also 4. There's symmetry here. Right, if I were to write 10 choose 3 without doing any calculations, I know that that's 10 choose 7 as well. Why? Well, 10 choose 3 is 10 factorial over 3 factorial times 7 factorial. So 10 choose 7 is the same thing. So there's this symmetry from the Pascal's triangle that's also in these binomial coefficients. So going back to the pattern that we have, right, we can write that x plus y raised to the nth power. What do? Well, I know that I start off with 0 of the x's and y is raised to the n. And how many of those will be? They'll be exactly 1, right? Remember, something choose 0 equals 1. All right. And then the next step, I'll have x to the first power, and I'll have y to the n minus 1 power. And what will the coefficient be? Well, it'll be n choose 1. And then the next coefficient will be n choose 2, and that'll be an x squared and a y to the n minus 2. And I just keep going, and again, I'll just know each of these coefficients by doing what we just did in factorial notation. And so when you look at it, this is summing them all up. I go from 0, I start counting at 0, and I go up to n, and I do n choose k, that's my indexing variable, x to the kth power and y to the n minus k power. So that's what we mean by the binomial theorem. And again, you've probably seen it as Pascal's triangle. What is the connection between the binomial theorem and probability? Well, what we do is we're going to let x be the probability of success. All right, so then x has to be between 0 and 1, and we'll let y equal 1 minus x, so y is the probability of failure. Then I have x plus y. Those are the two outcomes that can happen, either x or y, and they add up to 1. So when I raise them to the power of n, any 1 raised to the power of n is still equal to 1. So this big long set of terms in the binomial theorem, each of them is an individual probability. in this probability experiment. So we can leverage that to do some rather cool and powerful problem solving. Before we delve into deep problem solving with the binomial theorem, I want to show you a little bit more about probability trees. So here we have a situation where it's a chess tournament and Blitz legend Hakuru Nakamura can either win, lose, or draw. Now, the draws, tying, is almost like a loss because in these particular tournaments you need to win virtually all of your matches. Out of 9, you probably need to lose no more than 1 or win 8 in 2 draws to at least be in consideration for winning the whole thing. So, but he's got 3 different outcomes, and let's just suppose in the last few rounds of these tournaments he has these probabilities, right? He's got a 75% chance of a win, a 20% chance of a loss, and a 5% chance of losing outright. So here's the situation with the probability tree. And what I want to point out is that the probabilities coming out of each vertex, so look at this vertex, right? And when I add up 3/4, that's 15 20ths, plus 4 20ths, that's 19 20ths, plus 1 more 20th, that's equal to 20 out of 20, which is equal to 1. So the probabilities coming out of each of the vertices have to be equal to 1. And notice that they're all the same, so at all 3 places, all 3 of these vertices as well, it's true. But we can also do conditional probability with probability trees where this changes, where we might have drawn a card and then there's 1 fewer of the hearts or the spades. So, but whatever probability tree I'm creating, I just make sure that when I come to this node and I observe the probabilities for all the edges that come out of this vertex, they have to sum up to 1. And when I do that, the result is rather cool. By the way, we were talking about this as a graph. This is a directed and it's a directed tree with weighted edges. And for us, the weightings are the probabilities. So let's animate what happens. So the question is, what about a win and a draw? Right? How many ways can a win and a draw happen, and what's the probability? Well, the first way it can happen is we go left and then to the middle, right? We get a win and then a draw. And to find the probability that this happens, what we're doing is we're going to multiply the probabilities along the pathway. And when I do that, I get 3/4 times 1/5 equals 3/20. Now the next pathway you can see is getting drawn here. So if I have a win and a draw, I could also have a draw and a win. And if I go along that pathway, notice that the same probabilities occur, but in the reverse order. Now instead of 3/4 times 1/5, I have 1/5 times 3/4. All right. And the key thing about these probability trees, once I set them up correctly, something really cool is true. Each pathway is an event set that's mutually exclusive with any other pathway, with any other event set. So if I want to find the probability of a win and a draw, I trace all of the pathways I can find that lead to the correct pattern, and then I just take the probabilities of the successful pathways and I add them. That's the great thing about a probability tree. I multiply along the paths to get the individual probabilities of the individual events. But to sum up some events, yeah, exactly. When I'm combining these events and trying to calculate what the total probability is, I am just adding. Okay, a couple more features of probability trees ought to be clear at this point. First of all, notice that I've simplified this tree. I'm only dealing with wins and losses here. I haven't included the draws. If you'll notice, I swept the draws, losing and drawing, into the same. Basically, in these kinds of tournaments, you need wins. So a draw is useful, but not always what you need. So given that, notice that the first thing I wanted to show you is that with probability trees, and especially the binomial theorem, I can separate events not into every possible outcome that happens, but into the idea of what's a success and what's a failure. Then I only have 2 outcomes out of every vertex. And this is what will allow me to use the binomial theorem when I have just a success probability and just a failure probability. And then the second point was that I can simplify probability trees. I don't always have to include every possible outcome that can happen at a vertex. I only need to model enough to answer whatever question I'm being asked. So remember that when you think about using a probability tree, do I need to draw an edge for every possible outcome? Or can I think about what success means and simplify my probability tree? Because the big idea is that making these trees with any more than 2 or possibly 3 sets of branches gets really, really tedious, especially if I have more than 2 edges coming out of each vertex. So, all right. So then to answer this question, he has a 3 in 4 chance of beating the players ranked from 2,400 to 2,700, and then we're going to do the same probability we did before. Win 3 of the 4 matches. These are the exact same pathways, right? Win, 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 loss would be right here, right? Just like the heads, 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 tails. Then win, win, loss, win, win, loss, win, win. And then along the right-hand pathway, we have to go win, win, win after the initial loss. All right. Well, these probabilities are all the same. Let's just look at this first pathway, right? I have 3/4 chance times 3/4 chance times 3/4 times 1/4. Okay, well, I have the same probabilities, but in a different order. 3/4, 3/4, 1/4, 3/4. Here I have 1/4, 3/4, 3/4, 3/4. Okay, so, oops, I've lost my iPad. The probability of 3 heads and 1 tail, well, there are 4 different ways that we found that pattern happening. So 4 choose 1 ways for it to happen, and when it does happen, it doesn't matter what order, we're going to have 3 of the 3/4, right? So that'll be 3/4 cubed, and then we'll have 1/4 in there one time. So we don't normally put that exponent, but I will just for clarity because they relate to these other values, right? So the 3 heads you can see this is the power of success. And by the way, maybe I should have put 4 choose 3. That might make more sense because then the probability of success. And what is this? This is equal to 4 minus 3, right? So the number of trials minus the number of successes is the number of failures. But the key, let me just switch this. The key is that I have 4 choose 3 patterns. I have this probability occurring. The probability of success occurs in the pattern 3 times, and the probability of failure occurs in there 1 time. Okay, and so that's how I can use the binomial theorem to solve probability questions. By the way, if we want to evaluate this, this is 4 from the 4 choose 3 times 3 cubed over 4 to the 4th. So this ends up being 108 over 256. And you can reduce that fraction, but you can see that all 3 wins happens, about 10/25. That's about 2/5 of the time. About 40% of the time, he's going to be able to win 3 of his 4 matches. Okay, so that's how we use a probability tree, and that's how the binomial theorem ties in. So when we can use the binomial theorem, we're talking about these probability experiments called Bernoulli Trials. So the key features to know when I can use the binomial distribution in probability problem solving is when I have a specific number of trials. I have to know ahead of time. For example, I have to know that there's a 10-question multiple choice quiz. I have to know how many draws or trials there are going to be. And then I have to have a fixed probability of success, right? This has to be fixed. It can't change every time. There can't be any conditional probabilities where the second trial probabilities are different than the first trial. So when I have these types of situations, we call them Bernoulli trials, just to identify, hey, the binomial theorem will work here. And then as we showed, we have the probability of success plus probability of failure equals 1. So I have something that's equal to 1 on the left-hand side. So I know that the thing on the right-hand side must also be equal to 1. And that's really cool because now these are all the different events that are possible. This is one success, and then somewhere in here I have a binomial term and these powers that equates to 2 successes and 3 successes all the way up to n successes. This is a fun, lighthearted example about a young man at UNG asking young women out on dates. And this actually happened in my class about 13 or 14 years ago. And we joked about it. It didn't actually happen, but we set up this idea that in the name of science, in the interest of science, this young man named Eric would go out into the hallway, and the next 5 young women that come by, he's going to ask them out on a date. And the question was, well, we needed a few things. If we're going to use the binomial theorem, we needed to know what the probability of success was. And so we supposed that Eric had a 20% chance of success, and that was fixed. And there were a couple of other people in the class. Lane was Eric's good friend. They were sitting next to each other in the front of the room, and Lane argued that 20% chance of success was way too high, that his buddy would have a much lower chance of getting a date. But let's just use 20% for the moment. And then there was a nice young woman who was also in the room, Joy, and we said, hey, Joy will go out in the hallway, and she'll make sure that the young women who are being asked out, they aren't already in a committed relationship. You know, if they're already in a relationship, then Eric's chances would be much lower of getting a date. And Lane said, well, it wouldn't be that much lower. And so anyway, we were joking around and having a good time. This is a thought experiment. It didn't actually happen. And we just used it as a lighthearted way to take a look at these binomial theorems. So let's just suppose that Eric does ask these women out, and he does have a 20% chance of success. And then what is the probability that out of the 5 attempts, Eric gets exactly 4 dates? Well, that would be amazing, right? If he only has a 20% chance each time, getting 4 is going to be a fairly small probability. But let's use the binomial theorem and look at these terms, right? So what we're saying is that there are 5 trials, and this is the number of successes, right? K equals 4, right? We're letting K be the number of successes. So if I have 5 trials, choose 4 successes, then I take the probability of success and raise it to the number of successes power. And then I take the probability of failure and I raise it to the probability of failures power. So this is what we mean by using the binomial distribution, right? We know about these patterns, right? This 5 choose 4 tells me how many possible patterns there are going to be where there are 4 successes and 1 failure. And then I know from the previous example that I'm just going to have this number of 1/5, right? I'm going to have 4 of them in different patterns, but they're going to be there. And I'm going to always have this 1/4, this 1 failure. So I think I just explained it, but now I've highlighted the important pieces of information in red. 5 choose 4, 5 trials and 4 successes. Chance of success is 1/5, and the chance of failure is 4/5. So the total probabilities are not very good. Like we said, if he's only got a 20% chance each time, the probability of 4 successes out of 5 is going to be less than 1%. So we can do this. What's the probability that Eric gets either 1 or 2 dates? We can do this in the exact same way. Right? We're going to do 5 trials, choose 1 success, right? So this is the number of successes, and notice that I have 1 success, and then 5 minus 1 gives me 4 failures. So I always take the probability of success to the number of successes power, the probability of failures to the number of failures power. The same thing when there's 2 successes, 5 choose 2, 1/5 squared, and 4/5 raised to the 5 minus 2, or the 3 failures power. And so just like with the probability tree, these are mutually exclusive event paths, right? I can have either exactly one success or exactly 2 successes, but if I have exactly 1, it can't also be 2. So since these are mutually exclusive event pathways, then I'm allowed to just add. I can calculate the probability of 1 success, the probability of 2 successes, and then just sum them up to get the total. So back to the chess example, if Nakamura's probability of winning in the final 4 rounds is exactly 3/4, find the probability that he wins at least 2 of the 4 matches. Like before, we're going to be able to sum up these terms because we're going to calculate the probability that Naka wins exactly 2, then the probability that Naka wins exactly 3, then the probability that Naka wins exactly 4. So here, and you can see that I've highlighted in red the number of successes, right? So the first term relates to 2 successes, the next term relates to 3 successes, and the last term relates to 4 successes. Notice this is 1/4 to the 0 would go here, but I haven't included it because anything to the 0 power is 1. Well, often summation notation is going to be a lot more helpful. So notice what we do. We're going to use k to be the number of successes, right? So I can run this summation from 2 successes up to 4 successes. So I take the number of trials, choose k successes, then the probability of success raised to the k successes power, and the probability of failures is going to be the number of trials minus k. So we'll raise 1/4 to that power. On a graphing calculator, we have a couple of functions. So we can use the sequence function, and also there's a cum sequence function which will do all of this at once. I'll show you, I'm going to go through the calculator in just a second, but let me just show you that there are 4 terms. So this first term here is typing in the function of the calculator, okay? And then we specify, after we specify the function, we specify the variable, and then the start, and then the stop. So the 2 and the 4, that's controlling the where we start and where we stop. And then this expression that we start with, it looks a little complicated, that's just typing in the binomial theorem term that we know is going to be there. So let me grab my graphing calculator and show you. Let's see if I can position this a little better. Okay. And so you should be able to see what we're going to do. So we're going to use this list button. So I'm going to go second, stat, and then I want to go over to operations. And the 5th one here is sequence. Now, this cum sequence will work. Sorry. Option 6, it'll do it all at once. What I like to do with option 5 here is I like to display all the terms. Okay. So sequence, and then I need 4 choose, so I'm going to go 4, and then math, probability, NCR, so 4 choose X, right? I'm going to use X as my variable because the calculator only has X, T, theta, and N. So we'll just use X as the variable, so think of it as K. So 4 choose K times, and then I have 0.75 raised to the X power, times 0.25 raised to the, and I'm going to put parentheses in here because it's going to be 4 minus x power. And let me get down out of the exponent there. And the comma is above the 7 key. So now I tell it, hey, x was my variable. I tell it I want you to start at k equals 2, comma, I want you to go up to k equals 4, close parentheses. And then when I hit enter, it will show these terms of the sequence. All right. So the first probability for n equals 2 is about 21%, and then the next probability where there were 3 successes is about 42%. Remember that you can always go math fraction mode, and it displays the 3 terms of the sequence in lowest terms fractions. So that's why I like using the sequence. And then that's not the answer, right? I know the individual probabilities for each of the 3 terms, but I need to sum them up. So here is how we do that. I just go back to second list. And if I go to math, I have this sum option. Okay, so it'll sum them up. So I just go sum, and then I want to sum the answer, right? So ants is down here, the negative number key. And so this will just sum the last thing that was there. Well, the last thing that was there was this sequence. And there we go. We see that he has a 243 divided by 256 chance of winning 2 or more. So that's pretty high. Again, can you do this using the Cume sequence? Yes. Sorry, if I scroll back up, then I just use Cume sequence here, and what it'll do is it'll give me the answer straight away, and I won't see these middle terms. Again, I want to show you the sequence because I find it helpful to look at the terms and make sure that I understand what the calculator is doing. That's a lot of information to take in, so let's finish with an example. We're going back to Eric's dates. Notice that we've changed to 20 trials and a slightly different probability of success. We're going to 0.1. So I've got a slightly different example here. And let's work these out. What's the probability that Eric gets no dates? That's k equals 0. Okay, well, the probability that k equals 0, we are going to take 20 choose 0, right? Out of 20 trials, there's 0 successes. And so I don't need the probability of success because it's going to be raised to the 0 power, right? All I really need is the probability of failure, which is 0.9 raised to the 20th power. As a matter of fact, I didn't even need this. This is equal to 1. 22, 0. We're on the far left of the Pascal's triangle, so that entry is just a 1. So the answer is just 0.9 to the 20th. Okay, so the next probability asked for is the probability that he gets at least 1 date. So that's the probability that k is greater than or equal to 1. So the probability that k is greater than or equal to 1, well, here we're going to use a summation, right? So the summation is going to take k from 1 up through 20. And at each step, I'm going to have the number of trials choose k, because k is the number of successes at that step. So this is going to be 0.1, the probability of success raised to the probability of success power, the number of successes power, and the probability of failure raised to the number of failures power. Okay, and we could do that on the graphing calculator, but we can also remember set complements, because the probability that there is at least 1 success is the complement of the probability that there are no successes. So we could just subtract this value from 1 to get the answer to part B. So this was, this was part A, and this is part B. So for part C, we have the probability that Eric gets exactly 3 dates. So when I have a single term, I like these single terms. What's going on? Sorry about that. When I have these single terms, probability of k equals 3, now I just have the number of trials choose the number of successes, So I have the probability of success raised to the 3 power because there are 3 successes. I have probability of failure raised to the 17th power because there are 17 failures. So this is how I write down the probability that I need. Part D, or 4, sorry, I guess I'm calling them 1, 2, 3, 4 over here and listing them as A, B, C, D over there. But what's the probability that Eric gets at least 3 but not more than 6 dates? Okay, this is going to be a summation, so I'll still call it D. If I'm going to do letters over here, I'll stick with that pattern. So the probability was that 3 is less than or equal to K, which is less than or equal to 6. Well, this is just a summation, so it's going to look like this summation up here, but with slightly different limits, right? So all that changes in the summation notation is that the K goes from 3 to 6. I still have probability of success raised to the kth power because K is the index here, the index variable that's indicating the number of successes, and I still have the probability of failure, which is 0.9, raised to the 20 minus K, because there are 20 trials, and if there are K successes, and there are 20 minus K failures. So we can use our calculators and that sequence function to go ahead and calculate this as well. And then the probability that Eric gets 5 or more dates. Well, hopefully this is becoming clear. This is why I wanted to go through one example where we sort of in rapid fire just write these down. What's the probability that K is greater than or equal to 5? Well, that probability is the summation from K equals 5 to 20. Again, 20, choose K. So this is why summation notation is nice. It's always the same, right? The form is always the same. Probability of success raised to K, probability of failure raised to trials minus K, so 20 minus K. So this is the correct answer on a probability test. This is the exact answer. This is an expression that will give us the exact answer, like the square root of 2 is the exact answer. And then when I'm estimating these, I want to do estimates on a test or a quiz to 5 significant digits. So if you're asked to provide exact probabilities, or you will be asked to provide exact probabilities, you need to be able to write this down, this expression here. You have to be able to write it down to get the correct answer. But there will be a point for estimating it with your graphing calculator. And why is it important to estimate? Well, you'd like to not come out with a number like 1.43, right? If you come out with this value from this expression, you don't have a probability. It's not between 0 and 1. So we always want to put this in the graphing calculator, get an estimate, and make sure that our answers make sense. So to finish the story about Eric and Lane, we were going over this, and the class had some fun, and people were taking notes, and we were finishing one of these examples. And I believe that the probability that we were dealing with was 1/20th, was 0.05. That's the highest number that Lane would go with. And so we had this idea. Well, what is the probability that Eric gets all the dates, right? What if all 20 women say yes? And the way we found out about this is I saw Eric and Lane, they were talking, and then Lane punches something into his calculator, shows Eric, and then Eric says something, and they both bust out laughing. Well, we've been having this joke involving the two of them going for the last 20 minutes of class, so I'm like, hey, you have to share the joke. Well, so what had happened, Eric said, well, what's the probability that all the women say yes? And so at 0.05, successes, so that raised to the 20th power, I think was something like, 9.5 to the negative 27. I mean, just some incredibly small number. And then what made them both laugh was Eric said, so you're telling me there's a chance. So quoting from that famous scene from Dumb and Dumber, where L, at least there's a chance. So again, please just take this lighthearted approach the way it's intended, just to have a little bit of fun. The key idea is to be able to use the binomial theorem to go ahead and write down these probabilities quickly and easily, and then make sure that you can use your graphing calculator to estimate them. Be sure to do your completion quiz, and I'll see you next time.